Hello everyone. Today we will step through the GSA tutorial to evaluate the grounding system performance per IEEE Standard 80. You can find this tutorial documentation on the tutorial links page, as well as going to the XGS Lab help desk where you can download the CAD files and proper documentation. To start, we have the GSA module selected, and we will go to the project information icon. This allows us to enter in our project name, as well as general information such as the fault current into this project, and this information can be saved for our automated report. You may also enter information such as the customer, designer, and site information that can be retained in the project file as well as for our automated reporting. Next, we will assign our reference standard, which for this tutorial we will use the IEEE Standard 80. And then we will go to the multi-layer model icon. Here we can enter in a soil model manually using the table, but more commonly we will enter in soil resistivity measurements using the soil resistivity analysis tool. Following the tutorial documentation, we can copy soil resistivity measurements from an Excel sheet, and using the table paste function, paste those values into our table. Here we can see the preview of the soil resistivity measurements, and following the tutorial documentation, we can assign a specific number of soil layers. Hitting the calculate, we can see an RMS error of 2.7%, and applying this, we can now go to the results group box and plot our soil model. Using the snap icon, you can retain this image for your automated reporting. Next, we need to actually import our system into our model environment. We can pull information from CAD files, such as is displayed here. Here we have red conductors representing the grounding system, blue conductor representing an external tank, and these circles representing the location of ground rods. Note that these are cells or block references that we will import. First, we need to navigate to the location of the project file. We will also need to specify the units that are used in that CAD file. And then we can import the pertinent layers for analysis. In this tutorial, we are going to pull the eGrid soil or eGrid layer, which contains the ground grid design. We will also need to use this delta Z in order to shift the grounding system 0.7 meters into the earth. Here we've assigned the horizontal ground conductor. Next, we will import the ground rods as a solid conductor with a 15 millimeter rod. We'll give these a unique tag name of rod and shift these 0.7 meters into the earth. We will call out the block name or cell name and the length of those rods. Next, we will pull in the tank layer, and this will give us those blue conductors or that external electrode. So we'll assign this as electrode 2, indicating it's an external system. Assign this as a solid conductor of 10 millimeters. And we can leave the tank and no need to do a vertical shift. Finally, we'll import the civil works layer, and we will use this background checkbox in order to assign this layer as a background element, meaning that the software will not incorporate those lines as a part of the analysis, but they will be visually displayed so that you as a user can determine where touch voltages may be applicable, such as by equipment locations. Once the system is imported, we will see a representation of our ground grid in the XGL CAD view. And here, if we tilt our view, we can see the ground rods are placed going into the earth. And here's the blue conductor representing our tank. Taking a top view of this station, we will now insert an energization or a fault current into our model. With GSA, we can select the energization icon, select a current, and assign the 5000 amp injection current specified from the tutorial documentation. Next, we will debug and compute our model. This will determine the impedance of our grounding system, which we will be using to incorporate into the split factor calculation to determine the expected total current going into the grid versus portion going to alternative paths. Note the calculation is completed and we have an Analysis tab and a Summary tab. Under the Analysis tab, we can go to the GPR and earthing impedance. Here we can see the impedance of our grounding system is 0.24 ohms, and I will call this ground grid. And electrode 2 we will refer to as the tank. So we'll take this 0.24 ohms and go to our split factor calculation. And because we specified the IEEE standard 80, we will use the IEEE standard 80's calculation references to determine an approximate fault current split. We will enter in the clearing time of half a second with an X over R as well to incorporate any decrement factor for that asymmetrical fault. For this application of the tutorial, we are using a 1.09 ohm and 0.208 ohm equivalent resistance corresponding to 2 transmission lines and 4 distribution lines. Note that this results in 4,229 amps being injected into our current of the total 5,000. Applying this, we can see our energization has now changed from 5,000 to the result reflecting the fault current split. And we can use the debug and compute once again to calculate the new ground potential rise and look into our touch and step voltage results. Here we can see going to the GPR and earthing impedance, our electrode names, we can rename them as the ground and tank electrodes. Mainly we want to see that the fault current has changed from 5,000 to 4,000. And other values we want to update are the conductor sizing, which we will use the 5,000 amp fault current for the single line to ground fault with a 0.5 second clearing time. From the tutorial documentation, we have a 25 kA double line to ground fault with 0.35 second clearing time. And this K value represents the fault split of conductors or the grid components. So a value of 1 would reflect a ground lead or equipment lead coming from a substation transformer or other equipment, while a 0.6 value would represent the current of the below grade components, or how much current those below grade components can withstand. Since the grid will make a mesh and current can go through multiple paths within that mesh. Note that you can use a smaller conductor with a smaller K value. We will also need to specify the compliance criteria, so this will require us to enter in the clearing time, and the permissible touch and step voltage limits will be calculated based off of the IEEE standard 80 criteria. Going back to our analysis, we can go to our area calculation, and this is where we will determine the areas where we want to evaluate touch and step voltages. We will follow the tutorial documentation and use a x0, y -10 as our origin point, and a length of 100 and a width of 80 meters for our area calculation volume. And we'll use a step length of 1 meter. So each of these little dots will represent a location where we were specifically calculating the Earth's surface potential. These values will be compared to the potential of our grounding system, and the difference of those will reflect our touch voltage. Here we are plotting a three-dimensional view of our ground potential rise, or the Earth's surface potentials. So if we zoom in on this, we can see our substation makes a plateau of the Earth's surface potential, and we can see the little indent that that tank provides for the Earth's surface potentials. We can save an image of this, or an illustration of this, by going to add a view. We'll call this our top-down zoom view, so that we can automatically go to this view and take a snap of that before moving to our touch and step voltages. Here we will look at the touch and step voltage safety plot corresponding to touching the substation equipment. Here we see green values representing where we are within compliance of IEEE standard 80, yellow indicates that we are exceeding the touch voltage criteria of IEEE standard 80, and there are no red areas in the plot, but that would indicate that we are exceeding the touch and step voltage criteria. Note that only the substation is compliant, and then areas where there are yellow, where there's no equipment to touch, we can still be within compliance of IEEE 80. We can take a snap of this plot. Note that we can change our electrode reference, such as changing it to tank. Now we will use the tank electrode as our reference for touching. So here we can see a very different safety plot is represented. And we can also use the all element in order to create a reach distance, such as a 20-meter reach distance, to look from the closest element or the closest electrode for referencing for touch and step voltages. Note that this is a mask so that it does not reflect the touch and step voltage magnitudes, but the relationship of the touch and step voltages relative to the compliance criteria that you have specified. Now we can go to the Summary tab, and here we can see in our gallery a list of the images that we have snapped, and you can use this automated report in order to generate a report of your grounding system that incorporates any information that you've included in your project file. This includes our safety plots that we took some snaps of at the end. Completing the analysis and following the tutorial documentation, we can place a line calculation, and we'll just place this across our substation and our tank and calculate our line potential and view this plot to represent the earth potential along the line, the relative touch potential, the relative step potential, and our relationship with the compliance criteria noted in these dashed lines.